Thank you for the kind introduction, Professor Kies. I'm a PhD student at the CRC lab. My name is Fabian Wermelinger, and in the next couple of minutes I will be talking about a solver for compressible multi-component flow, where we put a special emphasis on hybrid architectures to offload the computationally intensive parts to the GPU accelerators. The talk is structured into 4 sections. I will start with briefly saying a few words about the flow model we use. I will continue with the considerations we have made to implement the solver. In the third part, I will show some performance figures, and finally I will show some simulations, actually one simulation we did for a collapsing cavity array. Okay, so our flow solver is based on the inviscid Euler equations, where we have conservation of mass, conservation of momentum and energy. The conserved variables here, rho u, and e, may represent a mixture of fluids. And to describe the interface we encounter in our flows, we use 2 additional transport equations which advect 2 scalar functions, capital gamma and capital pi, which depend on material parameters, lowercase gamma, which is the ratio of specific heats, and pc, which is a correction pressure used to model tensile stresses in liquids. Both of these parameters must be determined empirically. Since we're interested in water-air couplings, we use a stiffened equation of state to close our system, which was introduced by Harlow and Amsden. And one additional assumption that consists in the model is that there is mechanical equilibrium across for the interface regions. That means that velocity and pressure are equal on both sides of the interface. We discretized this system of equations using a diffuse interface method, which is based on a uniform 3D structure grids. To discretize the spatial terms, we use a cell-centered finite volume method. To discretize the time domain, we use a third-order low-storage Runge-Kutta time stepper. And for the following slides, the vector u will express the cell-averaged conserved quantities of our system I introduced just a couple slides ago. So we use a method of lines to discretize the system of partial differential equations, where we discretize the right-hand side here using a finite volume method, as mentioned before, which will reduce the system to a system of ordinary time-continuous differential equations. And one of the key part of our solver is actually to compute this right-hand side, which consists of mainly 2 parts, which is a high-order reconstruction, which we use to reconstruct cell-averaged quantities at cell faces, pointwise values, which are denoted here by u minus and u plus. This operation consists of a stencil, so we use a high-order Wien-05 reconstruction, which consists of a 6-point stencil to reconstruct u minus and u plus. The second step consists of evaluating a approximate Riemann problem. In our case, we want to compute the flux that crosses the cell faces, and we do this by using an HLLC numerical flux, which is superior for interface problems. Okay, I would like to move on now to software design considerations we have taken for our solver. So the main computational task in our problem is the solution of this system of ordinary differential equations. By using this third-order Runge-Kutta time stepper, we can decompose this problem into 3 stages, where each of the 3 stages requires one evaluation of this right-hand side function, which is a computationally expensive task. So our our strategy to solve this problem is to store the data R and U on the host CPU, where we have a large amount of memory available, and we want to offload the computation of this right-hand side to GPU accelerators, sending back the data and performing the scalar AX plus Y on the CPU again. In order to fit into the smaller memory domain on the GPUs, we perform a domain partition where we partition the domain into smaller segments. If the total domain consists of n cells, in terms of memory layout, we need 7 arrays in total to represent the 7 quantities in our conserved vector. Each of these arrays is of size n, and we store these arrays in the structure of arrays layout in the memory. So how do we process the segments on the CPU side? So first I will talk about the left part of this figure, where we introduce a working set which consists of 2 pinned memory buffers, which we use for asynchronous communication with the GPU. And similarly, on the right side for the GPU, we use another set of working sets, which consists of a global memory array, which we use to communicate with the host, and some additional memory space, which we later use for texture references, which we use as read-only inputs, read-only input for our stencil scheme. So the way we process these segments on the CPU is shown in the box here by algorithm 1. I need to mention that the vector v here denotes either one of those 7 arrays I mentioned before. So, and the superscript k denotes the index of the segment. So we start by copying the data from the host domain into the first pinned buffer of an available working set, and followed by enqueuing the necessary GPU tasks to compute the right-hand side for this particular segment. Next, we loop over the remaining segments. If there was a previous segment, we synchronize with the CUDA stream to get the data back from the GPU, and we perform the scalar AX plus Y computation, which is denoted by the update here. And then we increment the segments and proceed in a similar way for all of the segments. And at the end, we still need to synchronize for the very last segment and again update on the host. On the GPU side, so we use CUDA streams for each of the segments we use one CUDA stream. So we process the segments on these streams. If a stream is dispatched and it's available on the GPU, the computation that are carried out are shown here by algorithm 2, which is basically the evaluation of the approximate Riemann problem on the GPU. Excuse me. So we start in the first step to convert the data from conservative variables to primitive variables. We're doing this in order to avoid spurious oscillations in pressure when we do the Wiener reconstruction. The second step consists of copying the data in the global memory array A into the texture into a texture region, which we bind to a global texture, which we then use for the stencil inputs, and then we process each of the 3 spatial directions sequentially, which is a dimensional splitting, basically. So the GPU kernels we use to process one of these segments represented in a CUDA stream is basically a set of 26 GPU kernels. So the one kernel for the data conversion from conservative to primitive variables, we have 21 Wiener reconstructions. So for the 3 directions, we have 7 quantities to reconstruct. And we use 3 HLC flux divergence kernels. And one additional kernel that is required is a data transposition for the HLC kernel in the X direction. We need this to ensure that we have coalesced memory access when we write back the data. So our focus is on lightweight GPU kernels, mainly because we need to reduce the consumption of hardware resources on the GPU in order to exploit enough parallelism in our scheme. We have tried a single fat kernel, which does all of the 26 kernel calls at once, but this results in a massive 255 registers per thread, and it just results in very poor occupancy on the GPU. Nevertheless, for the HLLC flux computations, we still use a fused kernel, which means that all of the 7 flux contributions in one direction are computed with one kernel. We do this because basically all of the fluxes require more or less all of the 7 primitive variables, and we do this in order to reduce read redundancy, which would again result in poor performance if we did the HLC for all of the 7 fluxes independently. So with this figure here, I would like to explain how we actually do the stencil computation on the GPU. The big block here denotes the texture memory we use for our scheme, and on the right side you see a small block which is in global memory, which we use for the ghost cells. So basically we have read-only texture memory, which we use for inputs of our the Wiener reconstruction, and we use 2D CUDA thread blocks to explicitly enforce temporal locality, which allows us to use the data cache on the GPU efficiently. In order to compute the 3D stencil, we apply a 3-pass scheme, and in each of the 3 passes, the 2D thread blocks are aligned in the normal direction of the traversal, which the figure here is shown for the x direction. And then at irregular domain boundaries, we obtain stencil data from global memory, which is shown by the blue cells here. And one other thing I would like to point out is even if we use this scheme for a fluid dynamics application, the technique itself is not depending on such things. So it is easily used for other stencil codes, provided they use structured grids. Okay, so now I would like to present some performance figures. We have run our code on PitStained. Here is a brief overview of what is available on one node. There is an Intel Xeon 8-core CPU. We have a Tesla K20X Kepler generation GPU. We have 32 gigabytes on the host side, DDR3, and 6 gigabytes of GDDR5 on the GPU. I have to point out here that this is focusing on the per node performance for the moment. So for one function evaluation of this right-hand side function, we measure a performance of 55 gigaflops flop per second for the conversion kernel, roughly a teraflop per second for the Wiener reconstruction, and about 430 for the HLC flux, which results in an overall performance of about 460 gigaflop per second. We have compared this number to our in-house multi-core based flow solver, which is called Cubism MPCF. This solver has won the Gordon Bell Award in 2013, and we find that for this partial offloading of the right-hand side, we find a partial application speed up of about 3.2x. We have performed the roofline analysis of our GPU kernels, which shows that all of our kernels actually exhibit excellent performance. There is slight deviation in the HLC seen here, which is due to the data transposition that is required to ensure the coalesced writebacks in memory for that particular kernel. The black square here shows the overall performance of the right-hand side computation, which corresponds to about 12% of the nominal peak on a K20X. Here we show time distribution we obtain for one time step. Here dt denotes the computation of the admissible time step for current step. Then the 17% corresponds to the data copies of each segment into the pinned memory buffers. H to D and D to H correspond to the data copies to the GPU and from the GPU. There is a slightly higher percentage in the H to D copies, which is due to the extra copies of the ghost cells to the GPU. And then we spend about 37% of doing computations on the GPU and about 15% of the Saxby update on the CPU side again. A bit more detailed what is going on the GPU. We see that for the copying for the use of texture arrays, we have to copy the data into a CUDA 3D array. And this is done by the CUDA API at the moment. And we see that this is actually a very expensive operation. And if I go back to the roofline again, we see here this black pentagon. This is an estimation of where the overall performance would be if we could neglect this high overhead, which is due to the copying into these CUDA 3D arrays in order to bind to the textures. A few short words about weak scaling. So our main focus for this paper was on the per node performance of this solver. We have a naive implementation of using MPI to scale across multiple nodes, but we do not provide compute transfer overlap at the moment, and this is already seen in the about 60% weak scaling we obtain. I have to mention here that we also observe a lot of contention on the network when we perform our measurements, which is shown in the mean time to solution and the error bars for which is the mean of across all nodes. Okay, so now I would like to move on to the last part, which is the simulation of a collapsing cavity array. The simulation setup consists of a domain of liquid water, where we submerge 10 air bubbles of a radius of about 125 micrometers. We use a planar shock wave upstream to force the collapse of these bubbles. The strength of the shock wave is about 400 bars, so the bubbles are in equilibrium at 1 bar with the liquid up here, and the pressure behind the shock is 400 bars. We have run the simulation on pit-stained using 64 GPUs, which resulted in a total resolution of about 4.3 billion cells. With this resolution, it accounts to about 128 cells per radius resolution for each of the bubbles. I would like to show a movie of the simulation where we render the pressure field and the isosurfaces of the interfaces. Orange pressures correspond to about 2,500 bars, and the green pressure field corresponds to about 800 bars. We can see a highly non-spherical collapse of the bubbles and also some pressure rebounds in the upstream field due to already collapsed bubbles. There is a velocity jet penetrating through the bubbles, which causes this non-spherical collapse, and we observe a maximum pressure peak for the very last bubble. Here are some more results. One of our interests in the simulation was to see the maximum pressure amplification for this case, where we define the pressure amplification as the maximum pressure we find divided by the shock strength. And for this case, for the last bubble, it's amounted to about 100, which means that the collapse of the last bubble was about 100 times stronger than the initial shock wave, which corresponds to about a maximum pressure of 40,000 bars. On the right side, we show some Schlieren visualizations on the XY plane, which are through the center of the domain. The top image shows the wave structure using the pressure gradients, where we can still see the leading shock wave. And the bottom image shows the interfaces, where we can also see the numerical diffusion due to the diffusive interface method we use. In terms of collapse times of the bubbles, we have run with the same solver a single bubble collapse using the same shock wave, but only one bubble. And for this case, the bubble collapse time has been measured to 654 nanoseconds. For the case of the cavity array, the first bubble collapses in about 688 nanoseconds, which is slightly slower due to the shielding effect of the downstream bubbles. We also found that successive bubbles collapse about 3 times faster due to the penetrating effect of the velocity jet that is induced by the collapsed upstream bubble. Okay, with this, I would like to come to a conclusion. We have presented a technique to solve stencil problems on the GPU using texture memory, where we used explicitly 2D thread blocks to enforce temporal locality of our solver. Our approach is general and can be applied to any problem, provided that they use structured grids. And maybe a quick outline to what we plan for future. We will certainly address an improved compute transfer overlap for our current MPI implementation. And one other thing we want to look at is to improve the memory layout when we bind to texture memories, where we can use some sort of blocking to get rid of the expensive CUDA API method we have to call every time. With this final slide, I would like to thank the people that have contributed to this project, and I would like to thank you for your attention.
Thank you.